Okay, so in this lab we're going to measure the speed of sound, and what we have here is a graduated cylinder. It's kind of hard to see against the background of the workshop. And then you have, hopefully you went and printed out your speed of sound data table right there. And if you look at this thing, notice we have some musical notes. CX, which is 1,000 hertz. There's no note called X. Middle C, A440, G, E, and high C. Sorry, this is higher C, this is low C. And I have a series of tuning forks that play these notes. So for example, here's A440. Sounds like that. Okay. And the frequencies are listed here. So the frequencies of hertz are 1024 for high C, and the lower C is 256 hertz. And then to calculate the period, how long it takes to make a wave, the reciprocal frequency is period in seconds. So, for example, 1024 hertz is 1,024 cycles per second. 1 over 1,024 is 0.00097 seconds per cycle. So what we're going to do is we're going to measure the wavelength of that tube by using a pipe. This pipe will reinforce the sound because it's related to how big the pipe is. So what we'll do is we'll have a variable size pipe by putting it in the water, and the water defines the bottom. So I can make a small pipe or a large pipe by doing that. So what I'll do first is, just for a demonstration, we'll do 440. Listen. See how it's louder right there? So that length from there to there is actually 1/4 of the wavelength. So I have all these set up in a series of how big they are. And what we're going to do is we're going to measure the wavelength in centimeters, and you have to convert it to meters. And then you have to multiply by 4 because we're only getting 1/4 the wavelength. So we'll start with 1,024 hertz. There it is right there. We'll measure that height from the water level to the rim in centimeters, and that height is 7.5 centimeters. I'll record that. Okay, so this is not very precise because, you know, it's a lot of eyeball work. Here's 1,000 hertz right there, and that guy is about 8.0. Okay, 512 hertz. Right there. Notice how it's getting longer each time, and the tuning forks are getting bigger, and the frequency is getting lower. So that is 15.8 centimeters. Okay, A440. There. A440 is, of course, it's better to do this with a partner so one guy can reinforce the sound while another guy measures. 18.5 centimeters. And then we'll do G, 392 hertz. Right there. And that is 20.6 centimeters. Okay, and we'll do E320. Right there. Okay, and that is 25.5 centimeters. And lastly, we got C256. Let's see if this even fits in there. Okay, it's going to be 256 is going to be bigger than the length of the tube. So the length of the tube is probably about 40 centimeters. So it's going to be higher than 40. So I'm going to put 40 plus, and I'll let you extrapolate where you think that point is when you draw a line through it. Because what you're going to do is plot this data. Notice I even made a graph where you could download. Okay. And here's period in milliseconds. So this period is 0.001, 0.002, 0.003, etc. And you can kind of see where the in-betweens are. And this is wavelength in meters. Okay, so don't forget to take those numbers over there in the data table and multiply them each by 4. And then you're going to plot a line. And when you find the slope of that line, this is meters, this is seconds, the slope of that line will be meters per second, which will be the speed of sound. Okay, please do allow yourself 2 significant figures in this problem. Okay, you're lucky you have that because of the way we measured it, but it's a fun lab. Okay, I'll post it out online.